talking first about the difference between statics and dynamics. We will come back to both of these topics throughout the course of the year. We're going to cover Newton's laws now as it pertains to translational motion. Now, the word translational motion means change in position, or that style of motion. But we will have to come back to this to deal with rotational motion. So although we will leave this topic and develop energy and momentum and collisions and center of mass, we will have to come back because, quite frankly, I'm going to be lying to you right from the very beginning. I'm going to start by drawing pictures of, boxes and objects acting on, having forces acting upon them. And I'll talk to you about, this case where we push on the box. The box might have some friction acting on it. We know it's got weight. We know there's normal forces, all these kinds of things. And I'm going to say that all boxes act the same. Bless you. But we all know that that's not true. That if the box looked like this and I apply the same forces, that these two boxes are likely to behave differently. And it has nothing to do with the fact that the forces are different. It has to do with the fact that the shape of the box and where I apply the force on the box does make a difference. And this is true for anybody who's ever pushed a freaking box before. You understand that this difference plays a big role in deciding maybe where you should push on the box. That you might want to find that it's better if you push lower down on a box like this to prevent it from tipping over. Or maybe your goal is to tip it over, in which case you're probably applying it in the right place. For the time being, we are going to use this framework to deal with all of our forces acting on the object at a single point. Thus, the free body diagram. But that's a bit of a lie. Bless you. So you guys are aware that this is of limited use. So what we're teaching right now is not the way the world works. Now, statics and dynamics are two parts of the same thing. You could say Newton's first and Newton's second if you'd like. That'd be an oversimplification, but it would at least get us an idea of what the difference is. To be clear, statics is covered by Newton's first law. It does not mean not moving. It means not accelerating. And I want to be very clear. Newton's first law wasn't his. Newton's first law is Galileo's. Galileo found, over careful measurements and an attention to detail, that if he had a system that had very low friction, that an object would continue to move indefinitely. He wasn't able to state things as clearly or as cleanly as Newton was, but what he did deduce is that the natural state of an object isn't at rest, which had been the primary idea up until him. Aristotle's idea is that everything was at rest and that they required impetus to begin moving, and that's not the truth. What Galileo found is that the natural state of being is in motion, is in a state of constant velocity. And being at rest is a subset of that motion. So generally what we say is that all objects have a general state, a natural state where they are in motion. That motion can be considered to be a velocity of 0, but generally we state that all objects exist in a state of motion. That is their natural state. And that state suggests that there is nothing acting on the system. It's changing that motion that requires a force. It's when we wish to change the natural state of an object that you must unbalance the forces acting on the object. And that's Newton's second law. Now, Statics covers why your chair is broken, right? The chair is attempting to keep you at rest. Those forces that the chair must apply in order to do so that the net force is zero may or may not be successful by the plastic part of the chair. If they're unsuccessful, the chair might break. Same thing goes with my door. My door handle's falling off again. Does so every year. Why? Because you're supposed to take and carefully turn the door handle and push outward on the door. You don't. You lean into the door handle with all of your weight, thinking somehow that if you lean on the door handle, you'll get out of the door faster. I'm not sure when you decided that would work. But you're not alone. For 15 years, my door handle breaks partway through the year. Might be a record, though, this year, because it might break before October. Normally, it's like February. So either you guys have gotten better at breaking my door handle, or it was never fixed properly from the end of last year. I'm going to go with not fixed properly from the end of last year. And generally, there are about 5 steps to solving a Newton's Law problem. That really does, unfortunately, make it sound easier than it is. But let's just say there's 5 steps. And the first one is the only one I will actually write down because it is the one that I think is missed almost all the time. And we skip over it, not understanding how critical it is to the framing of the problem. However, when faced with a situation, it should be your goal to be able to describe what you think is or is about to happen. Before you start any problem, you should decide, what do you think is about to happen? It's amazing how many people skip over this step and just jump into the next part, which is drawing a free body diagram. Don't do that. Sit and think for just a moment what's actually happening. Our first problem is going to be something incredibly straightforward and is not particularly interesting, but is a good place for us to start because it tends to be the kind of problem that students get wrong. We'll start with the elevator problem. It's a relatively straightforward question. It's in every single textbook. It's just how these things should be started. There's a cable attached to the elevator. If you wish to go up in the elevator, you're going to go in the elevator, push the button, and the elevator will have to accelerate upwards until it gets to its cruising speed. It'll then travel at its cruising speed until you reach your destination. And then the elevator has to slow down and to bring you to rest so the doors can open and you can get out. That is the motion of an elevator. During that time, there's going to be tension in this cable. Let's say that the elevator has a mass of 200 kilograms, which is a terribly light elevator, but who cares? And let's say that you are a svelte 60 kilograms. Nothing but muscle, I'm sure. Now, I'm going to state the question. If the elevator accelerates upwards at 2 meters per second squared, what is the tension in the cable? If the elevator accelerates upwards at 2 meters per second squared, what is the tension in the cable? So this brings me to step 1 of the problem. After you've read the question, you should, of course, stop to think what is going to happen to the elevator. And I think we already have the answer. But would somebody like to articulate what's going to happen to the elevator? All right, so how many of you agree the elevator is going to go up? Excellent. Is its velocity going to change? How do we know its velocity is going to change? Yeah, I told you, it's going to accelerate. That's a good start. So we know this is a dynamic question, not covered by Newton's first law. Now, this is interesting. I'm asking for the tension in the elevator. Is the cable attached to the person?
No.
Do I have to worry about the person's mass?
Yes.
Now, this is a harder question and one that I want to make sure we're clear about. Does the cable cause the person to accelerate upwards? Now, again, your textbook talks about the difference between objects and agents. And although I'll use these words belie something deeper that's not being discussed yet, Newton's third law. But it's very fundamental to the way in which Newton's second and first law have to be used. Newton's second law and first law can only be applied to a single object at a time. It is the M in F equals ma. You must deduce what the object is in your problem. But it is the object to which Newton's laws apply. The agent causes a force. The object experiences or receives a force. I would say that if your entire system accelerates in the same way, you can treat it as a single object. But you need to be careful when you apply that rationale to every problem. So always take a moment and consider, does your system behave in an expected way, and is it accelerating in a uniform way? I think we can treat the box as a 260 kilogram box. I think we'll be okay, unless the problem was about the person and not about the box. So, question 2, free body diagram. You must make a free body diagram. And you know I am going to be vicious about your free body diagrams. You know that. In your free body diagram, you're going to be asking yourself a series of questions. And when you deal with those questions, be very clear. So, question number 1, are there any fundamental forces acting in your system? That's always your first question. It should be one that you do not take lightly. And look, E&M folks, start worrying about the fact that you have multiple forces acting in your system. I'm not trying to take over the class and talk about E&M, but you guys can't be in E&M without also knowing that there's going to be some stuff about gravity in there. So you're the only, your class can have all of the forces working. But in mechanics, we only have one fundamental force to worry about, and that's going to be gravity. So when you identify that gravity is a force acting in your system, in this case, the object is still going to be the elevator and the person. The agent is the earth. It is the earth that causes that force. And that will be a force that is directed straight down. I will label capital W as weight. Just a point about symbolism and symbolics here. I use single capital letters for each independent force. It's not how your book works, and it's not how a lot of the books work. A lot of the books use a capital F for each force, and they subscript it with what force it is. I find that to be cumbersome, especially if there's more than one tensions. Having force of tension number 1 and force of tension number 2 can begin to get very cumbersome. But be aware that my way is not ubiquitous and is not what's done in most textbooks. So you choose what you want to do, because you will not be wrong regardless of this choice. But there are a lot of things that W could stand for. It can be the unit of watts. It can be the quantity of work. So there are reasons why you might want to use a capital F for all of your forces. I do it this way because I think it's cleaner. So I'm going to stick with it. Weight is always calculated as mg. Now this is when we're assuming we're dealing with simple weights. That's not the force of gravity. If it's the force of gravity, we'll have to use Newton's law of gravitation. But we're dealing with weight, mg will be just fine. So after you've discussed the first force, the fundamental forces in your system, when you've exhausted that, then you move on to the contact forces. you should go down and deduce whether any one of the individual contact forces exist in your problem. So start with normal force. Is there any surface in contact with your object that could exert a normal force? Now, in the condition that we have right now, I don't see a surface. There's a surface in contact with the person that exerts a normal force on the person. But when we're dealing with the elevator as a whole, I don't see a normal force acting on the elevator. Now, if this was a elevator shaft and there were walls on either side, that might be trickier. There might be some kind of normal force from the walls of the elevator on the elevator. But let's, for the time being, keep this a simple problem. Fair enough? So I see no surface in contact with the elevator, therefore there's no normal force. So I can strike off the first of the contact forces. The second contact force is tension. You should be looking for any cables, wires, cords, handles, anything that could impart a pulling force to your object. In this case, we have a tension. The tension force is acting upwards on the elevator, but be aware all tension forces act in the direction of the cable. So you need to be cognizant of the direction of your tension force. Now, I note to draw this arrow as an arrow that is greater than the weight. This is because, based on question number 1, what do I think is about to happen? I think the cable is going to pull up on the elevator more than the weight is pulling down. I was told the elevator accelerates. So I am accepting the idea that it is the tension that causes the acceleration. Third contact force is friction. Is one surface sliding past another? Now, there can't be friction if there's no normal force, so us ruling out the normal force automatically ruled out friction. But if I go back to that statement, that if I had a wall here, there could be friction. You could be scraping against the wall on your way up. Real elevators are in an elevator shaft. Real elevators do make contact with their walls, usually on rollers of some sort. So real elevators do have frictional forces that act on them, especially their safety systems, which are often clamping systems that clamp onto something on the side of the wall should the cable fail, break, or the engine itself fail or break. So be aware that that's likely a real force on a real elevator. But in this elevator, since there's no normal force, there's no frictional force. And the last of the forces that we'll be probably dealing with will be drag forces. It's our object moving through some fluid that would impart drag. And there could be realistically a drag force acting down on an elevator. It probably would not be very great since drag is proportional to velocity or velocity squared. But that doesn't mean it couldn't happen. If I was to draw it, I would draw another arrow downwards. And here's where I want to be careful. There's 2 ways to draw a secondary force acting in one of the dimensions. One is to stack your arrows, like so. One is to draw them side by side. I move between both of these, depending on what I feel like doing that day or that moment. So be aware, neither is wrong. And both will be accepted by any grader on the AP exam. But you can't ignore scale, no matter which one of these 2 you choose to use. The scale of this arrow should start at the end of the first if you're going to stack them. And its length should still be proportional to the size of that force. All right, getting back to where we were. I have gone through and identified all the potential forces that could act on my system. But that is not an exhaustive list. You guys understand there are other forces we didn't talk about, and they could be acting on our system. For all I know, my elevator could have rocket engines on the bottom that apply thrust to the bottom of the elevator. I wouldn't want to be in said elevator. It probably would not be very enjoyable for very long, but it's plausible. I mean, if you've ever watched Willy Wonka, you understand that, his elevator, which is not called an elevator, by the way. Here we go. Now that you guys have put together a straightforward free body diagram, the next couple of steps are these are often forgotten, but they are kind of like a big deal. The first thing you should do is apply a coordinate system that you will use to deal with your forces. A coordinate system is an XY plane. So you should choose a coordinate system. Now, this is an arbitrary choice. You can choose any coordinate system you'd like. I mean, I could, if I really felt like it, choose a coordinate system at an angle and make this the Y direction and this the X direction. Now, that'd be stupid though. The object is accelerating in both the X and Y direction, making this the least useful coordinate system possible. So what I would do is I would encourage you to create a coordinate system, but create a coordinate system that fits your problem and makes your problem simpler. Now, this is a choice you make. Not all times is it going to be the same choice. There are some choices that work better than others. Sometimes the problem just sucks and you're going to have to suck up the fact that there isn't a great coordinate system to make your job easier. However, when you settle upon a coordinate system, I would encourage you, if possible, to choose a coordinate system aligned with either the motion or acceleration of the system. That will significantly alter your amount of time on the problem. So I have chosen to make the positive Y direction upwards. And I've chosen to the right to be the positive X direction, even though there are no forces to the right or left. Your coordinate system dictates positivity and negativity of your vectors. Also, your coordinate system creates the one-dimensional problems that you will have to solve. Which brings me to the next step, which is all forces must be broken down into one-dimensional components that are aligned with your coordinate system. That's way complicated, but I'll say it again. All forces must be broken down into one-dimensional components that are aligned with your coordinate system. That part's hard, and you really need to be careful about making sure you do your trig right. Monitor what theta is or what phi is. Understand that your component vectors should act along directions that are aligned with your coordinate system. I mean, this one is really a nothing kind of question. I've chosen a coordinate system that's already aligned with my forces. That doesn't stop me from recognizing that in this case, the net force on my system is the sum of two forces. I am going to focus on the net force in the Y direction. And this is a vector. And although I'm not even applying Newton's law yet, I'm just saying in the Y direction, there are two forces that are acting on my system. This is the net force on the system. And in that, I have applied direction to the vector quantities. All forces are vectors. I chose up to be positive, so weight's negative. Once you've applied a coordinate system and broken your vectors up, you should determine whether this is a Newton's first law problem or a Newton's second law problem. You should have already determined it. You should already know what's going to happen. However, it is quite possible you don't know the answer to that question. What if you're trying to figure out if the forces are strong enough to cause the object to move? Under those circumstances, you don't know. So, a simple rule of thumb is you must assume it's a second law problem unless you absolutely know it's a first law problem. Again, assume second law unless you absolutely know first law. In this case, we know it's a second law problem. Now, once you're here, you've done all the hard work for Newton's laws. Generally, at this point, there's something missing and you're trying to figure it out. In the case of this problem, we wanted the tension. We know the weight and we know the mass, and we were given the acceleration of the system. The math part will almost always be the easiest of the parts. Unless, of course, numbers aren't given. And then it could get quite tedious. But hopefully in this question, you guys all see that you can solve for the tension. Before you walk out, though, one question I would ask, just to throw you off, is what is the net force on the system? Thank you. The net force on this system is 520 newtons. MA is net force. We could have answered that before the problem began. The tension in the system, though, was 3120 newtons. All right.